Good morning or good afternoon, everyone, and welcome to the third of our technical presentations on applications of SCAT or EMT simulations for different power system related applications. The first webinar covered the background on electromagnetic transient simulations itself. Second webinar was on simulation applications for renewable integration. Today we are moving a little bit away from general applications, and we are going to talk a little bit about machines, machine modeling, and application of synchronous machines and induction machines for power system studies. So here is the outline. We will briefly talk about how machines are mathematically represented in PSCAD-like programs, EMT-type programs. We might briefly talk about the differences between EMT-type program, mathematical representation in EMT-type programs, and RMS-type programs. Then I will show you. I will take a simple example and show how the machine models can be, connected and set up for a simulation in PSCAD. I will show you a very simple single machine infinite bus type example, which I always use. I have been using for the past 20 years whenever I want to study, add a machine model to my simulation network or the circuit. I will show you how I use my simple example case and just copy paste the structure of the model into the case, into this circuit that I want to study. We will talk about data entry, typical data, and also I will briefly discuss about the accuracy of our model. The PSCAD machine models are extremely well tested and accurate. They have been in use for 30 years, but we still get questions from our users about its response, mostly because sometimes the data entry is wrong and certain things are not clear. So we will discuss how accurate our model is, and I will show some examples and hand calculations. We will also talk about, for the mathematical discussion on modeling, I took the synchronous machine as the example. We will also discuss induction machines and maybe permanent magnet machines, but we won't go into the details of mathematical modeling of these types of machines because the approach is similar to that of the synchronous machine. Once we have that discussion, once we discuss key aspects, key points about synchronous machines and also induction machines, I will go and show you probably about 6 or 7 examples where the machine models are used for practical studies. So that's the plan, and let's move on. So we will start with a little bit of a mathematical discussion on how the synchronous machine is represented in EMT type programs. What you see on the left hand side, like it's pictures from of a synchronous machine. You can see the windings, like it's a complicated arrangement of coils or windings, both inside the stator and in the rotor. But for modeling purposes, and depending on the design of the machine, the winding type can be very different. Like you can have so-called lap windings, concentric windings, wave windings, and nowadays people are coming with even different novel designs. But all these machines, for all mathematical modeling purposes, these windings can be represented by a number of magnetically coupled coils. So here what I have shown is the machine mathematically can be represented by 3 coils or 3 windings, winding A, winding B, and winding C, that represent the 3 stator windings. Then winding number 4 shown here represent the DC field or the field winding. One thing you have to remember is, unlike a transformer, here some of the windings are moving or rotating. In this case, the field winding is rotating. So it's the position of the field winding. The magnetic axis is the magnetic axis of the field winding, which is through the winding, is constantly changing with respect to the stator windings A, B, and C. Okay, that's an important point. So essentially, this angle between the field winding, the axis of the field windings, is generally referred to as the D axis or the direct axis of the machine, right? And 90 degrees to that is the so-called quadrature axis or the Q axis. These are just mathematical concepts to help us simplify the modeling process. So the D axis or the field winding is constantly rotating. In steady state, it rotates at a constant frequency corresponding to your steady system frequency. So here I have 4 equivalent windings representing this complicated, complex actual winding structure. In order to make the behavior of the machine, response of the machine, in order to more accurately and realistically represent the response of the machine, we need to model some other phenomena outside of these 4 windings. And the most crucial out of those phenomena are the so-called damping or the damper impacts, right? So if you look at the actual construction of a synchronous machine, here what I have shown on the right-hand side is the construction of a pole face. In addition to the DC winding, this is the DC winding, right? There are so-called damper bars short-circuited at the 2 ends. So these bars are short-circuited at the ends. So during transients, when the machine speed deviates from the synchronous speed or the rated steady speed, currents gets induced in these shorted windings, right? And that would have a stabilizing effect on the transient. So if the machine is speeding up, the induced currents would contribute to a torque that would try to slow down the machine and vice versa. In addition, currents can also get induced in the iron of the rotor, eddy currents. So the impacts of these have to be considered to have a realistic machine model, response of a machine model. So the dampers, the effect of dampers are mathematically modeled by including 2 short-circuit windings, or sometimes 3 short-circuited windings, called the D-axis damper KD and the Q-axis damper KQ. So these are not real windings. They are windings in the mathematical model that tries to mimic the realistic behavior of the machine. So in this case, you can say the voltage current relationship between different windings can be represented by a matrix equation where R and L are termed as the resistance matrix and inductance matrix, right? So this is simply V equals IR plus d by dt of Li, right? We are used to calling this equation, we are used to the equation where we say V equals Ri plus L di by dt, right? Here it is d by dt of Li. That is because both L and I are time dependent. The L is not a constant. We will see why. So in this particular case, this is a system of 6 coupled coils. Phases A, B, and C, that's 3. Field winding, which is a real winding, number 4, and the 2 equivalent dampers, right? So if I go back here, the machine for modeling purposes is represented by like I said, 6 coupled coils, A, B, C, F, K, D, and K, Q. Right? So the resistance matrix is simply a diagonal matrix representing the winding resistances of these. The inductance matrix consists of self-inductance terms, self-inductance of A, B, and C, LA, LB, LC, LF, LKD, LKQ, as well as all the mutual couplings between different windings. So that's why this is a coupled coil representation, MAB, the mutual inductance coupling or inductance between windings A and B. Some terms you can see the mutual coupling terms are 0. That is because there are windings that are on the rotor, the field and the Q-axis damper, they are 90 degrees apart. So we say that there is no magnetic coupling. That's why the mutual inductance there is 0. And also note that the D-axis and the Q-axis, or in other terms, field winding and the damper windings are constantly rotating, which means their position with respect to the stationary stator windings are constantly changing. Okay? Which means the magnetic coupling, for example, between field and A winding, the mutual inductance between field winding and A winding is not a constant, right? When the D-axis aligns with A axis, you have the maximum flux linkage, maximum coupling. Whereas when the D-axis is 90 degrees, there is no coupling between field and A axis. There is some coupling between field and B and C axis windings. So that results in, because the rotor is change in position, the terms of this LA, MAB, some of these terms are time dependent or rotor position dependence. For example, LA can be written as LA, you can show or approximate, LA can be approximate as a constant term plus a cosine term where theta is the position of the rotor with respect to phase A axis. Oops. So now, in order to solve this equation, in order to find the machine's response, you have to solve this equation. So we can assume that we know the terminal voltages, like the time variation of the terminal voltage or the input voltage, let us say, is known. You can solve this equation to find the current. That's what the SCAT machine model does. Here I'm just trying to show, I think I already explained why some of these inductance terms are time varying. You can easily figure that out from this equation, this diagram, right? Phase A and A dash represent the phase A winding in this simplified example, right? The flux due to currents in phase A would go like this, or go like this, same direction, because it's a stationary winding. But depending on the rotor position, this flux has to either go through the magnetic path provided by the rotor, right? So the reluctance, the reluctance of seen by the flux is less in this case, whereas here, when the rotor is positioned like this, the flux has to cross a large air gap. So the inductance, reluctance, and correspondingly the inductance of phase A is position dependent, is rotor position dependent. Right? So now we have to solve this equation, which is a little bit complex because now L is not constant, right? But in order to get the machine currents, you have to solve this. There's no other way. What we do sometimes is, in order to make this, the solution of this equation less complicated in computer programs, mathematically less complicated, we do a linear transformation, one-to-one linear transformation from the so-called ABC domain to DQ0 domain. It's a linear transformation. When you transform this equation, right, to DQ0 domain, you get the same set of equations, but in DQ0 quantities. So IABC are converted to IDQ and 0, VABC converted to VD and VD, VQ and V0, and you will get a number of equations, right, corresponding to the stator windings and the rotor windings, right? So whether you solve this equation or whether you directly solve this equation, you will get exactly the same answer, right, to the decimal point. So here what you do is you convert ABC to DQ0, solve the equations in DQ0 domain and reconvert it back to AB0 using the inverse DQ0 transformation. Whether you do this or that, you should get the same answer. Remember, it's a linear transformation. So now, just very briefly, I don't want to go deep into this. If you take RMS programs and EMT program, in RMS or EMT, the rotor side equations are modeled just like they are, no approximations, right? Stator side equations, like if you look at VD, there are three terms. VD is equal to IDRS, that is the resistance drop. Then you have this term called lambda Q multiplied by the rotational speed, flux or flux linkage multiplied by the speed. This you can say is the induced voltage because the windings are rotating, right? You have a rate of change of flux which induces a voltage just because you can have a DC current or a DC flux, but you are just moving the position of the windings. So that gives you a rate of change of flux and induces a voltage. It contributes to the induced voltage, right? So this is called the rotational term. This term is the Faraday effect or the induced voltage term because, like, if you apply a AC voltage or AC current, a time varying current, there will be time varying flux. Even if your machine is not rotating, even if you hold it stationary, the time variation of the current and the flux can induce a voltage. So this is the Faraday's effect, induced voltage term. This is the rotational voltage term. In RMS type programs, this term is neglected. The rotational term is always there. The induced voltage term is neglected in most RMS formulations, but luckily this doesn't, like it, for most of the studies that we do, neglecting this term in RMS does not contribute to a big, it's not a major assumption, right? So RMS and PSCAT, for most purposes, most benchmarking should give close results, but you can't expect identical results because there are some differences. Okay, so these are the electrical equations of the machine. Then you have to also solve the machine. In order to solve the electrical equations, you need to know the position of the rotor. You need to know the position of the rotor with respect to a reference location point, because all these L terms are position dependent, right? So you must need the position of the rotor in order to solve this equation, right? So the mechanical structure of a thermal generator or a hydro generator is pretty complex. There are a number of masses. The generator is a huge mass. Then there are the turbines, which introduce mass sections, and they are all connected by shafts. And these shafts are not rigid. They are elastic shafts. So there is interaction between different masses. right? And we refer to them as torsional interactions. But for most studies, we don't need to consider torsional interactions. For most stability-like studies, we lump all these masses into a single rigid mass, right? And once you do that, you can write the mechanical equations, the input mechanical torque minus the electric torque generated by the machine windings is equal to J d omega by dt. If you want, you can include the friction and windage, the damping term. Generally, this has very negligible impact, and I normally ignore this, right? So your mechanical set of equation response is given by the acceleration torque, which is input torque minus electric torque. Electric torque has to come from currents and voltages that are calculated by solving these windings, the equations. J is the inertia of the machine, omega is what you are trying to solve for. Once you solve this set of these equations, you have the full solution of the machine for that time step, and you keep solving it by extending the time step. Now, in terms of data entry, the real machine, the real system, you have to deal with inductances and mutual couplings between the actual windings, right? But if you look at the machine data sheet, you will be entering the data such as the leakage inductance, of course, which is real, then D-axis reactance, Q-axis reactance, transient and subtransient reactances, different time constants of windings in the machine. So this is what you will enter into the machine model. This machine data is entered in terms of D and Q quantities. And there is a direct relationship because ABC to DQ0 is a linear transformation. There's a direct linear relationship between what you enter and the ABC domain inductances and mutual inductances. For example, the field open time constant, TDO dash, right here, is simply the inductance of the field winding divided by the resistance of the field winding. Like all of these are related. I don't want to go into those details. This is for your information. So that's some background on the machine model. Now let us look at SCAT. There are three main models that you would probably use. Synchronous machine, and this synchronous machine can be customized to represent a thermal round rotor machine or a hydro machine like salient pole machine. Gen raw and gen sal, like in RMS terms. You can simply enter the data to make this act as one or the other. We have an induction machine, and this machine can be used to represent both a wound rotor type machine, right, where you have the rotor windings coming out, or if it is a squirrel cage machine that you are studying, you simply select to short the rotor windings. Then it mathematically it will behave as a squirrel cage machine. Right. Then we also have a permanent magnet machine, which is very similar to the synchronous machine. The only difference is you don't have a field winding here, you have a permanent magnet. So our machine model, I think this is an important point. It has been in use for over 30 years. I have been looking after this machine for the past 20 years. I hardly changed anything, right? The person who wrote it 30 years ago did a great job, and we don't want to touch that because it has been validated over 30 years. Almost all major power system projects, large HVDC schemes to evacuate large generation, like they were all designed and studied using SCAT's machine model. In recent times nowadays, like there are so many vendors coming up with different wind turbine concepts. They all use these vendor models are validated against field recordings. And if there are shortcomings in our machine models, major shortcomings, we would have shown up. So our models, we stand very strongly behind our machine models. Synchronous machines, they always work together with, exciter and governor models, and sometimes power system stabilizer models. In our master library, we have provided almost all standard exciter governor models, the standard IEEE exciter governor and PSS models. And if you go to our help, for each type of model we provide, you can figure out what the block diagram looks like underneath and so on. But now it's pretty common to have, especially in Australia, for example, like most of the exciters governors are non-standard, right? In that case, when you want to model those non-standard models, you have to build the control blocks yourself by using the control blocks in the master library. Connecting control blocks is simple. You look at your block diagram and just connect the blocks, but it takes a little bit of effort to back initialize or make sure that the control blocks gets initialized to an expected initial condition. If you don't do that, if you don't back initialize these custom models yourself, it might take a while before these controllers bring the output to the expected steady state, and you might have to run the simulation for a little bit longer time to get it to the stable operating point. There is also a danger if you don't do the back initialization. There is also a danger always that it will never reach the steady point. So I'm not going to talk about back initialization today. That we have technical notes and examples which we can provide upon request. It's not difficult. But our standard models, the back initialization is pre-programmed, and if you tell the model the initial conditions that you want it to operate at before you apply faults or something, the models will go through the pre-programmed back initialization routines and give you the expected steady output right from the start. This is the example that I'm going to show you later. And this is the example that I always use when I want to add a machine model to a circuit. I always open this case that I have and I copy the machine and the exciters and the governors. That way I don't have to worry about always connecting these exciters, governors, and wiring them. They are already done. You will see now in this example, I have exciter AC1A. If your exciter is AC2B or something like that, all you do is you can click here and select that exciter. I will show you. So you don't have to rewire. One thing you have to always also remember, or it's a good practice to remember, like you will have to enter the machine data, the machine electrical data, XTs and XQs. Be mindful of your data entry. These XTs, XQs, TDO double primes, for practical designs, they fall within a typical range, right? So sometimes your data sheets may not give you, there may be errors, mistakes in your data sheets provided. You have to be mindful in order to get the right response. For example, if I see TDO double dash or TDO dash as 0.3 seconds, I would question that, right? So this is also good information, and in a technical note that I will show you, all these are listed, right? You have all this information. So I will show you this example a little later. So what I have shown here is you can provide the initial conditions to the machine to make it operate at a predefined initial P and Q set points. Then in this case, I have applied a fault and just I'm looking at the response. We will look at this case later. Like this is just a hand calculation that I did some time ago or some years ago. Like you may remember this equivalence, steady state equivalent circuit of a salient pole machine, right? People sometimes question, oh, I entered the correct data, but I don't think the machine is giving me the right conditions or right results or whatever. So sometimes we have to show, we just can't say, hey, go figure it out, our machine is accurate. We can't say that, we have to prove that. So we have Excel sheets and hand calculations to show that in fact, if you enter the data, SCAT will give you the correct steady state response. We have also done extensive testing to show that SCAT will give the correct transient response as well. What you see here are the three waveforms following a terminal three-phase to ground short circuit, right? You can identify in this waveform the so-called sub-transient period, the transient period, the decay of field current transient, and so on. You can see this from the waveforms simulations in SCAT. But you can also, we have also verified, and I will give you the technical note where all these calculations are done. We have also verified that these response, the sub-transient period, the transient decay period, the field current decay, the peak field current during the transient, they all follow expected values as per theory. So that's what I have shown here. We have validated this model, like I said, extensively. You can either trust us, or when you have time for your own knowledge, it's probably exciting, especially for me, to go through these equations and verify that things do work. Okay, so that's some background and theory on the synchronous machine. Induction machine, like the concepts are similar. You have the three-phase windings, you have three rotor windings that are not supplied or connected to, in general, if it is a wound rotor or a squirrel cage operating in normal applications, you don't connect the rotor to a supply or DC field or supply, right? You just short it, right? So you have three windings and three shorted windings. So again, a 6 couple coil situation, you can write the inductance equations, resistance equations, solve the equations to get the response. I won't go into that. I will probably, though, discuss some important, useful facts that might come in handy when you do studies. These are the equations, these are the details that would go into the time domain equation. Solving the time domain equation will give you the transient response. We also talk of this induction machine in terms of its steady state equivalent circuit, which is this. Now, R1 is the stator winding resistance. R2 is the rotor winding resistance dash, because the value is referred to the stator. X1 and X2 represent the leakage inductance of the windings, stator and rotor. XM is the magnetizing branch or the magnetizing winding, magnetizing branch, equivalent magnetizing branch. For most discussions, you can actually ignore this XM for most transient discussions. And then you also have in the equivalent circuit You also have this term R2 dash divided by S. S is the slip. Slip is, unlike the synchronous machine, induction machines always operate with a slip. The speed of the machine is slightly different, either lower or higher, below or above the so-called synchronous speed. We don't want to go into details because in this discussion, but synchronous speed is the speed of the rotational speed of the resultant magnetic flux. When you excite phases A, B, and C with sinusoidal balanced currents, a magnetic flux, a magnetic field will be created, and this magnetic field will rotate at a constant speed. And that is called the synchronous speed. Synchronous machines rotate exactly at the synchronous speed in steady state. Whereas induction machines, must operate with a slip, a small speed deviation. So based on this equivalent circuit, we can derive the torque speed characteristic, steady state torque speed characteristic of the machine. This is the equation or approximate equation, and if you plot this, you will get the red curve. When you depending on your R and X values, the shape of this curve could be different. This is the so-called starting torque. This is the peak value here is the so-called pull out or the peak torque. And for steady operation, you have to make sure that the machine operates in this region. So essentially this region, because you're operating in this region, the operating slips are relatively small, right? This is your synchronous speed, this point, 1 per unit. Your operating speeds or operating slips are very small. The speed always is very close to 1 per unit of the synchronous speed. That is one characteristic of the machine. Probably another important point to remember is, let us look at these waveforms. Like this is, let us just say that we have a induction machine operating connected to a wind turbine. Induction machine operating as a generator, right? So let us see what happens here. At this point in time, there is a fault in the system. So the voltage drops. At this point, the fault is cleared. When the fault is cleared, you want, as a system operator, system planner, you want these machines to come back to stable pre-fault operation as fast as possible. Okay. However, what happens is, during the fault, the machine cannot push power out, so the wind turbine is still pushing in mechanical power. So the speed, machine speed will increase, machine will accelerate. Right? During the fault period, the machine will accelerate. We cannot do too much about this. It will accelerate. When it accelerates, what has happened is the slip. When you clear the fault, the slip has increased. See? Synchronous speed would have been somewhere here. The slip was this before the fault. Now, when you clear the fault, when the system is trying to recover, the slip has increased. What happens? So when the slip increases, when S goes up, R2 dash over S would come down, right? The effective resistance here will drop at this point when the machine is trying to recover. So this will increase, this whole thing will decrease, which means the currents I1 and I2 through this loop, you can ignore XM for now. the current I1 and I2 will increase, right? Which means the reactive power consumed inside these leakage fields, X1 and X2, which would be I1 squared times X1 plus I2 squared plus X2, would increase, and the relationship is, remember, I1 squared, not just even linear, right? So at this point, when the machine is trying to recover, when the system is trying to recover, because of this slip increase and the resulting decrease of this effective resistance, reactive power consumed by the leakage fields will increase significantly, as you can see here. See, and when machines or loads draw reactive power, that will obviously delay the voltage recovery, right? So this is an important point. This is why regions with large air conditioning loads, air conditioners driven by induction machines, have poor voltage recovery or voltage recovery concerns. This is why type 1 wind turbines were just the turbine directly connected to an induction machine, and induction machines stator directly connected to the grid went out of favor, right? Those type 1 or type 2 wind farms, during fault recovery, show poor response. So 10, 20, 15 years ago, type 1 wind farms were fine because you hardly had maybe more than 1 or 2 wind farms in your whole system. But when wind became more popular, penetration became larger, like the system planners wouldn't allow this delayed voltage recovery. So that's why type 1 wind farms are now probably not even heard of in Europe, North America, Australia, and places like that. Delayed voltage recovery. Now, another common application of induction motors is to study motor starting, right? When motors start, once again, when the motors start, what happens? When the motors start, during the starting period, the speed is not close to 1 per unit at all, like you start from 0 speed. So the slip is extremely high, right? So during the acceleration period, until the motor comes to its steady speed, this is low. The starting current could be high, which is not a problem for the motor, but when you have high starting currents, when you start very large motors, it could create power quality issues because of voltage dips. So I will show you an example. So two common applications, one in AC load representation, motor starting, and also definitely wind turbines. So those are that's some background on machines. We will take a 1 minute break for me to have some water, get my thoughts together, and then next I will show you some simulation examples covering model setup, model benchmarking against RMS results, some examples where synchronous machine is used for Blackstar Restoration studies, an example where we studied voltage flicker due to a compressor. The compressor was driven by a synchronous machine. I will show you the example and discuss how the model was set up. Sub-synchronous resonance and torsional interaction is also a very common application, but I will not talk about it today because we have a webinar directly, totally dedicated to this topic. Then I will show an example with the induction motor starting and fault recovery, and also another example of a type 3 DFIG type wind farm. Like, I mean, again, we don't want to go into the space too much time on that because we have many examples, and this very descriptive, what I think is very descriptive technical note available, right? So this is already available on our website for download, but I will definitely add this to the package that will come after this presentation for you to download. So it explains step by step how to set the case up, enter data, and so on. As you can see, I will show you, like you do have to enter the machine ratings and so on, machine ratings from the data sheet, and then the machine data in terms of XDs and XQs that you have to enter. It's very straightforward. But you also have to tell the machine, right, the initial condition. Like you also have to tell the machine the initial operating point that you want it to operate at before you apply a transient, before you apply a fault. Because especially machines, the response following a fault would depend on its pre-fault condition. For example, machine that is loaded close to its rating is likely to go unstable following a fault compared to the same machine operating at a lower power output, power reference point. So it's important before you do a transient study that you get your machines and essentially all your system elements to be at the expected initial conditions. So this machine provides you an input field where you have to enter the expected initial conditions. You can enter it in terms of the initial voltage magnitude and phase, or expected P and Q output. There are different options. Once you enter those information, and if you do things right and follow the instructions, or just copy paste this into your case, you will have very little trouble getting this model to work at the condition you want, initial conditions you want. So here's another example very similar to what I just showed you. Let me run this case. Again, a synchronous machine with a exciter, governor, blah, blah, blah. Let us assume that I entered the right data. And when I run the simulation, see, in the first example, things would have converged to a steady state, right? Here, like, see the speed, like power, reactive power, if you zoom in, doesn't converge to a steady state. The oscillations are extremely small, and sometimes you may not even notice it unless you zoom the waveform, right? But if you zoom it in, see, if your scale is such, you may not even see what's happening. It looks very stable, right? But it's important to make sure that it is in fact stable. When people see things like this, they always blame the model. They say, oh, your machine model is unstable. This is not a model problem. This is a real system problem. If you see oscillations like this, don't like investigate. Like your system is likely to have a oscillation issue, right? So in this simple example, let me turn this switch on and run the same case. See, stable. All I did was add a power system stabilizer, right? So I just want to highlight that just because you see oscillations, like don't blame the model or think that it's a model problem. It could be an inherent problem in your system. Second example, again, we have a technical note is related to the machine's response during faults, right? I'm not going to go into, I won't open this case, you can test this out for your own information and learning when time permits. Just wanted to highlight the technical note is there, all the details are there, all the calculations are there, and the example is there for you to study it on your own. Next, I will look at model benchmarking. Right now, in like last 2-3 years, many parts of the world, like USA, Australia, England, like the system operators wants your models benchmarked, tested before any new connections are approved. So one thing is to verify that the synchronous machine, or in other cases wind farms, comply with grid codes, the power ramp rates, current injections during faults, frequency response are in compliance with the expected grid codes. One other requirement is also like you have to use people have to do EMT and RMS studies. So they want to make sure that RMS models and EMT models pretty much give comparable responses. So you want to benchmark the results of RMS and EMT models, right? And ensure that the errors are within a narrow error band, the black envelopes that you see. When you do, like, I mean, for synchronous machines, PSSC or RMS, PSCAT results should be very close. So I'm going to take this example and show you some points that you may want to keep in mind. One of the things to keep in mind is most of these benchmark tests are performed on simplified single machine to infinite bus type systems, like idealized circuits, and that could sometimes give you issue problems. Then also remember, like in PSCAT or EMT, network dynamics gets into the picture. For example, the offsets in currents, right, show up in PSCAT, whereas network dynamics don't show up in RMS type programs. So because of that, you may have differences, right? So let's look at this this example. Like this was from one of our users, and what happened was the user could not get good comparisons. So he sent us the case, we took a look at it, and first thing I noted was, see, in the RMS program, the fault was applied at 10 seconds, and the fault was cleared after 0.1 seconds, right? So in real life, this doesn't happen. You don't have self-clearing faults, for one. You have something tripping. But for benchmarking, this is what people do. So if you look at this, I don't know if you can see this or not clearly. If you look at the first graph, what is this? Yeah. So if you look at the first graph here, you see the the currents, IA in blue, IB and IC. If you look at IA after 0.1 seconds, the current still has not decayed sufficiently. The DC offset has not decayed sufficiently for the current to cross the zero crossing, right? So even though you tell the PSCAT or EMT program to remove the fault, in EMT programs, the currents are interrupted always at a zero crossing, right? So in PSCAT, the current will not be interrupted after 0.1 seconds. It may wait for the current zero, and if, right? So in this case, I think the red phase experience a current zero because it's symmetrical. So the fault on that phase would be cleared, but the other phases would continue to conduct towards the fault until they come across the zero crossing, right? This is when in the model, when I used almost zero fault resistance. right? Now, if I add a very small fault resistance, like see, the blue curve also decays and things would, the fault will be cleared after 0.1 seconds as you expect, as you define in this time fault time logic. But if you didn't pay attention, if you don't look at all these things, these are the loop things that you can get stuck on. And these things happen because the circuit is so ideal. You are applying a fault right at the machine terminal. There's hardly any resistance to damp out the transient. So I thought that this would be useful information for you to have keep in mind. And in this particular case, you can see the comparison is pretty good. I think this is acceptable. Maybe we can retune to get a better match in initial conditions, but generally what I say is if you get these type of responses, that's pretty good. So this is the example case which you will have inside this green circle is my machine. And in order to, there are many ways to, efficiently do benchmarking. But here what we have done is we have recorded the RMS results into text files. And these text files are read directly into PSCAT using this component. Okay, so the RMS results are read and directly fed into the PSCAT simulation so that you can plot and compare them while you run the PSCAT study. The second example I'm going to show you is a setup that you would use to perform Blackstar restoration studies to verify that the black start, like when the system goes black, you have to restart your system and you have plans for that. And you have to do studies to verify that the plan would actually technically work. So here what we are trying to verify is using 1 out of 10 generators in a large generating station, using a 90 MVA generator in a large generating plant, can I energize my transformers without causing, so here I energize the transformer, and in this particular scenario, what I would look at is, would the voltage drops due to inrush current be too much to trip my under voltage protection? So step by step, first, can I energize the transformer without tripping the settings of the generator? Because normally you don't do this. Normally you would energize the transformer from the system side and synchronize from the generator's low voltage side. But under Blackstar, it's different, and your protection may not have been set up to account for that condition. Then you may also want to start studying, okay, can I energize the second parallel unit without causing sympathetic inrush, right? Then energize reactors and so on. But an important point is, can I also energize a long transmission line to go to my loads or go to my next generating station where I can connect 2 generators and then keep on energizing the rest of the system. So here, using breaker BA1, at this point in time, I'm energizing the line, no loads, just energizing the line, right? So you will have the switching transients that would be limited, high frequency switching transients that should be limited by the surge arresters. You have to look at all these things. We will discuss switching transients in a separate presentation, so I will focus on a more slow dynamic concern. When you energize the line, like without any loads, the long line is pretty capacitive. So reactive power would be injected back to the system by the line, right? Which would cause the voltage, the RMS voltage, to go up, right? So now the generator will have to control that voltage through its excite action. So you can see the field EF tries to bring the voltage down by reducing the field current and the field voltage, right? So there may be under excitation limit, there may be limits, right? You may not be able to drive the field all the way down to zero. There may be a limit here, which means the voltage, the RMS voltage, would not come down as fast, or maybe may not even come down to 1 per unit again. If the excite action is slow, right, depending on how the response your excite action, depending on the response of your exciter, the time duration where your voltage, the steady temporary O voltage, remains high, the time duration where the temporary O voltage remains high will depend again on the excite action and the length of the line. And this may violate your equipment safety, right? So through the study, you would look at how high your temporary O voltage would go and how long it would last, right? Depending on your observation, you might go back and say, hey, I can't energize this long line with just one generator, right? You may have to change the plan and decide to have two generators energized and connected in parallel in order to do all these energization routines. So these are the things that you study with during a Blackstar restoration. Again, this example will be provided to you. That's this one. Number 3 example is again a study we did some years ago at an industrial location where there were very large, I can't remember the exact rating, few megawatts, very large compressors at a steel mill or whatever, right? So the compressors, their load characteristics change over a rotation compression cycle. So when you compress, you need a lot of current, a lot of torque, but as you come out of compression, right, you don't need that as much current or torque. So that is the load or the compressor load characteristics. So when the current requirement of the load changes like this over a rotation cycle of the machine, right, that can impact your voltage drops, your voltages, right? And these are like the compressor is the RPM is low, right? So the corresponding voltage variation can be in the range of 8 to 10 hertz. 8 to 10 hertz is the worst for visible flicker. And in this particular case, the customers near this site experienced voltage flicker. They had to design a SVC to mitigate flicker. But in order to design SVC, first you have to model this flicker phenomena correctly. So here's how it was done. Once again, this is the representation of the transmission system. You don't have to model a lot of details because we had field recordings of the flicker, and by modeling the system to this extent, but modeling the synchronous machine, maybe the exciter, but most importantly, the torque characteristics of the compressor. This is how we model the torque characteristics of the compressor accurately. We were able to reproduce what we observed in the field. So once you do that, then you can add SVCs, SVC controls to mitigate flicker. So in this case, the actual torque, speed, torque, time characteristics of the compressor was used as the input to the machine as the machine talk. So we had to go through this little calculation in order to convert the datasheet values to a time domain input. What I have shown here are the field measurements, and if you run this case, you will see that PSCAT results are comparable. Okay, I said that we will not talk about torsional interactions, SSR, because that's a separate topic. And finally, I will show you very quickly 2 examples with the induction machine. I won't be able to provide this case to you because this comes from a real system. So at this location is an oil pumping station, right? So at oil pumping station, there are many tens and tens of motors of different sizes. Some are very large, few hundred, like closer to maybe even a half a megawatt. The others, there are smaller motors. What happens is over a day, they may start some of these motors for 5 minutes, then boost the oil pumping, stop the pumping action, then a few minutes later start another motor, and so on. So at an installation like this, there are large number of motor startings that takes place. Every time you start the motor, remember, when the motor speeds up, the slip is high, it will draw a large starting current. See, the large starting current is not of concern for the motor, but these are weak grid locations. These motor pumping stations are at weak locations further from the main transmission grid. So the customers, the households and industrial customers nearby would experience these type of voltage dips in their home. And if this happens many times a day or many times an hour, that is a power quality issue. So the utility will have to, depending on the magnitude of the voltage dip and the duration, the utility will have to limit the number of allowable motor start operations, or force the customer to install soft starters, power electronic based soft starters. So in this particular example, we had to very accurately model the motor, right? We had to match the exact torque slip characteristics, because if the utility put restrictions, when the utility puts restrictions on the customer, they are going to sometimes go to court, right? So we had to be very diligent, do a lot of data mining, and make sure that what we are doing is accurate. So the findings of this study were, when you start motors of different sizes, what are the expected worst case voltage dips at different customer locations in the system? I will provide you a motor starting example with the download package, but maybe not this one. Second example, again, this comes from one of our training tutorials. There's nothing really to talk about here. Like, this is a little bit of a transmission system. There is an induction machine. Sorry, there's a synchronous generator. There's a type 1 wind farm, which is an induction motor, and also a load represented by an induction motor load. So let us say a industrial load, or an area heavy with AC, air conditioning loads, right? So in this example, there is a fault in the system. Just to keep things simple, I self-cleared the fault. When you get this case, maybe you can clear the fault by opening breakers here at the 2 ends of the line. But what I wanted to show you is, oops, the delayed voltage recovery. See, the increased reactive power consumption of the two machines, and delayed voltage recovery. And this delayed voltage recovery, the poor reactive power response, is because the rotor winding is just shorted. In a synchronous machine, the field winding or the rotor is connected to an electric supply, the DC field. So you can control through the field winding, you can control your voltage response or the reactive power response. Induction machine, you can't do that, right? Your field wind or the rotor winding is just shorted. So that's why type 1 machines went out of favor, but the type 3 DFIG became popular, because in DFIG, like, the rotor winding is not just shorted, it is connected to a supply or to the grid through a power electronic, back-to-back power electronic inverter setup. So by controlling the power electronic inverters, you can actually inject currents to the rotor winding and avoid this from happening. You can actually control the reactive power, right, of the type 3 or DFIG following a fault clearance. So type 3 became popular for that reason. And again, this model of a type 3 wind farm is available to you for download. I will clean up what we have in the download section and provide a cleaner model to you. This is a pretty good type 3 wind farm that represents like the choppers, the DC link, the converters and controls, and again the induction machine is a central part of this design and the setup. Okay, so I hope the examples were interesting, the theory was useful, and with this I think I will stop the presentation and hope to see you again in about 2 weeks on our next presentation. Thank you very much. We will, within a week or so, we will make these PowerPoints and the presentation and examples available for you to download.